All right, hello, welcome to my channel. My name is Thomas, and this is an educational channel. Today is video number 127 on the reciprocal system of theory. We're getting toward the end of this interview, 1984 interview that he did with Jan Sommer, and it does a good job of just kind of going over the general issues with the theory. This is the reciprocal system of theory, which is Dewey B. Larson's creation from back in the 20th century, from when he had his first inklings of it about 1930, all the way up until his death in 1990. He was feverishly working on writing books for about the last 30 years of that. The first 25, 30 years, he was really kind of just trying to derive the theory using induction and then applying it using deduction. And the basic idea behind the reciprocal system is that we live in a universe of motion. It's not a universe of matter. It's not a universe of energy. It is a universe of motion. Matter and energy are merely just kinds of motion. And motion is the relationship between space and time. That's implying a ratio or a fraction. Motion is a fraction with time as the numerator and space as the denominator, or vice versa, either one. And therefore, space and time basically have a reciprocal relationship with each other, and hence the reciprocal system. Now, what we know about one reciprocal, we also know about the other, in the same way that 2/3 and 3/2 are reciprocals of each other. They both have a 3 and they both have a 2. And in the same way, what we know about space is that it's 3 or more dimensions, and therefore time is also 3 or more dimensions in its right context. What we know about time is that it's flowing or progressing. It's always getting later and later. Larson calls that clock time. And therefore, there is also a clock space, the progression or the flow of space, which means that space is always getting farther and farther apart, observed by the Hubble telescope in the recession of the distant galaxies. So there's clock time and clock space. And the three-dimensionality is what Larson calls coordinate space and coordinate time. And time and space are also quantized, meaning that there is a minimum unit of time and space, nothing less than that. Anything less than that, and you move into the other realm. So if you go less than 1 unit of space, you are in a realm of nothing but time. If you go less than 1 unit of time, you are in a realm of nothing but space. And if you have 1 unit of space and you have 1 unit of time, you link those together, 1 unit of space per 1 unit of time, you have the speed of light. And so the speed of light is really the one of the universe. And but this one, and this is a universe of motion. So in the universe of motion, it's not zero that is the background, the 0 point, so to speak. It is 1 that is the 0 point. And so you're basically using, instead of you're using arithmetic addition and subtraction, you're really using multiplication and division. When you have a 0 neutral point, as Einstein did in his universe, and Newton as well, then you have, 0, you have plus or minus those different entities that faster than 0 or slower than 0. I guess it wouldn't be within the realm of motion, but the magnitudes would be plus or minus. Whereas if you have a center of 1, then you're talking about multiplication and division. So you would have 2 and 1/2 as being, with the 0 midpoint, you have 0 plus 1 and minus 1, plus 2 and minus 2. But with 1 as the center, then you have 2 and 1/2, then you have 3 and 1/3, then you have 4 and 1/4. Those are the reciprocals. Those are the uh, equal distances from that center. And that center is the speed of light. So in Einstein's universe, the speed of light is the maximum speed of the universe. In Larson's universe, the speed of light is the midpoint of the universe, or the null point, or even the origin of the universe. And there is actually half of the universe that is actually moving faster than the speed of light. And then there's the half that we're familiar with that's moving slower than the speed of light. But the brilliance of the reciprocal system is that even though we don't know anything about this faster than the speed of light realm, we can extrapolate to figure it out, because we know what's going on in the slower than the speed of light realm, and we can just postulate that what's going on in the faster than the speed of light realm is exactly the same, except for the inversion of time and space. So whatever's going on in this slower than light sector, all we have to do is invert the fraction, and we get to understand what's going on in the faster than speed of light sector. So that enables Larson's reciprocal system to penetrate into areas that modern science cannot, especially life phenomena and mental phenomena, and then eventually even spiritual phenomena. Okay, now we're going to take over on this interview. He just got done talking. Now the other postulate of Larson's is highly disputed by even his strongest adherents, where he claims that the universe adheres to the laws of commutative mathematics, and that its geometry is Euclidean. Euclidean being basically x, y, z coordinates, coordinate space. And Larson here kind of admits that he doesn't really even think that the universe is Euclidean, but it's the easiest way to posit his theory. And that, if he assumed a different kind of geometry, it would just be more cumbersome for the person who's trying to learn it without really conferring that much of a benefit. So here he says, the problem is that we have 3 dimensions open to our perception. The person who's trying to understand that is trying to put it in his 3 dimensions of perception. And if it's something that won't fit into that, he gets the wrong idea. So, the questioner was really asking him why he didn't try to explore all these different non-Euclidean geometries to find out a better solution, given that his system doesn't really fit with this 3-dimensionality, because he has what you call a scalar motion. That's clock time and clock space, and the scalar motion is best to envision as taking a balloon, putting a bunch of magic marker dots on the balloon with a magic marker, blowing up the balloon. When you blow up the balloon, all of the dots are moving away from each other, but in no particular direction or in all particular directions. And so that is a scalar motion, a motion that has a magnitude, but it doesn't really have a direction. The only direction is either in or out, whether you're blowing up the balloon or sucking in the balloon. And that's how time operates, clock time. But that motion itself is a 1-dimensional scalar motion, and that requires 3 dimensions of XYZ coordinates to represent it. And so those other when you have 2 other dimensions of scalar motion, a 3-dimensional scalar motion, it can't be represented in the reference system, not in the one that he's using. And so the questioner was asking him, why don't you use a different geometry that might be able to represent some of this stuff? And he says, not really, because it'll just get too hard for the reader. And so Jan Sommer, the questioner, then says, "It just takes some getting used to, I suppose." I'd like to talk about the various advances that you made in the 25 years since the first book was published. In my view, the most important has been the concept of distributed scalar motions and the intermediate regions. Larson: "Well, I don't know. After you've cleared up a subject, then the difficulties kind of recede into the background. Of course, it's a continual process. Just on this latest book now, The Universe of Motion, which is on astronomy, I would say that there is no chapter in which something hasn't been cleared up during the writing of the book. It's been a few years now since I wrote Quasars and Pulsars, and of course, that only affected part of the area covered in the new book. So that much of what I'm dealing with now has never been considered by me specifically in astronomical terms." Just as an aside, Larson actually predicted the existence of quasars years before they were actually discovered. And he predicted many of their qualities in quite a little bit of detail as well, if you believe in quasars and pulsars at all. Okay, now back to Larson. What I've done is to apply the previous physical results to these astronomical problems as I've gone along. And of course, I've changed my outlook on some things that I perceive more clearly now. The question of the white dwarfs, for instance. I had a rough diagram in the structure of the physical universe that indicated how those objects would move on the color magnitude diagram. And the same general principle still applies. But the path on the diagram is different now in some respects because some of the points cleared up. A great many things that showed up in the course of writing this book simply fitted in with the findings that were made in the studies of other physical areas. Take, for instance, the question of natural units. I found during the physical study that whenever we come to a critical value of some kind in the physical realm, we are almost always, probably always, dealing with either a natural unit or a small whole number of such units. So here in the astronomical situation, I was able to take advantage of that. And because I found in the diagram, take advantage of that, and because I found in the diagram I first drew for the globular clusters that the three critical points there were related in such a way that the vertical distance is half the horizontal distance. So it became rather obvious that this was 1 unit and that was 2 units. By recognizing that, even though I still didn't know, or I still don't know what that unit is, it's a compound unit of some kind. I was able to reverse that over into the white dwarf region and draw the diagram for the other stars. That's purely a result of this finding with respect to the natural units that we have verified in the physical world. Just to make another aside as far as the white dwarf star, Larson says that the white dwarf star is the result of an explosion in time, not in space. An explosion in space would be something like a supernova. The star just explodes in space. But if it explodes such that it's faster than the speed of light, meaning that the explosion is occurring in the cosmic sector instead of the material sector, in the faster than the speed of light sector, where the relationships are in time instead of in space, then the explosion occurs in time, an explosion in time. And when you have an explosion in time, what you actually, because we don't see time, we only see space. And so when you have an explosion in time, you see the inverse of that in space. So what happens when a an explosion occurs in time is that the star implodes and it becomes super, super small and super, super dense. And that explains for Larson the white dwarf star as well as things like pulsars and quasars. Okay, a quasar is basically an exploding galaxy, where a white dwarf is an exploding star, and a pulsar is a special kind of exploding star. Okay, back to the questioner. I've seen the theory's accomplishments, but the establishment scientists are apparently looking for something else besides. I talked to a historian of science in Princeton about your work, and the first question he had, what predictions does it make, and have any been confirmed? That's how they evaluate a theory. Well, I mentioned those that you list in quasars and pulsars. Larson, well, of course, there is a whole chapter in that book on predictions. Actually, as far as I'm concerned, the emphasis on predictions is misapplied. I am not saying this to excuse not having predictions. The theory makes predictions all along the line. You could say that the entire physical universe is a prediction from the postulates. But actually, what we are doing is not so much going out into new territory as consolidating the existing material. While you find somebody like the man you're quoting that hinges the thing wholly on predictions, you will find equally competent scientists who will point out that what we need now is not so much to go out into new territory, but to understand what we already know or think we know. And that really was the content of that quotation I made from Richard Feynman, in which he said that the next big advance would be the qualitative explanation of these things for which we already have these equations. So I would be inclined very much to downplay the prediction idea. As far as the predictions are concerned, certainly we have done plenty of predicting as far as the quasars and pulsars are concerned. I didn't define the quasars specifically or the pulsars specifically, but I did predict the existence of the class of objects and gave the principal properties of that class of objects. Now, I have also done some predicting that is not recognized at the moment as predicting, but that's just what it is. For instance, I've developed quite a few points in connection with what I call magnetic ionization, and I've applied it to a good many problems. Now, the existence of the magnetic ionization is not recognized at the present time, so that is a prediction. One of these days, there will be some method devised of actually measuring it. That then will appear as a prediction, whereas now it doesn't. It appears as something I have grasped out of somewhere that people don't quite understand. This subject we were discussing, the meaning of the interregional ratio, that is a prediction, that there exists a physical constant that the scientists so far have not recognized. The existence of what I call the time region, the region inside unit space. That's a prediction. The books are full of predictions, but at the moment they have not recognized those things, and they don't recognize them as predictions. The scientists of 100 years from now may look at it in a totally different light. And here we are less than 40 years later, and hopefully we're capable of looking at this in a different light. Now, this is interesting because I have talked to other scientists as well, and that's what they have focused on. What kind of predictions does he make? But they're not even recognizing that he's making predictions because they're thinking he's just pulling it out of no place. But like I said, you have to read a number of his books before you recognize that he's applying these things consistently in every realm. He's not just pulling it out of someplace. He's using a method that we're not familiar with. And so that's kind of his idea of the time region. I mentioned if you are in a realm that is less than the speed of, or less than a unit of space, then you are in a realm of time only. Larson calls that the time region. And so the time region is a small region that is within the overall, space-time region, which actually Larson calls the time-space region, which makes it cumbersome. And over here, if you are in less than a unit of time, you are in a region of nothing but space. Larson calls that the space region. And the space region is a little subset of the overall space-time region, which is actually probably he should have called the time-space region, or maybe come up with a different term. Again, a lot of the problems that we have for understanding Larson have to do with terminology and just the different nomenclature that we're used to with the legacy science. And so, in order to really learn the reciprocal system, you have to throw all that aside. You have to just say, okay, I don't understand this. I don't have any preconceived notions. I'm just trying to understand this. And so if I don't understand something that he says, I will just move on and just let it percolate in the back of my head. Don't judge it as being right or wrong, but just, try to, work it out. Just humor him for a second and let him say his piece before you decide to criticize it. Okay, we're going to leave it there, and we will take over and possibly finish this interview tomorrow. Thank you for tuning in, and I hope you have a great day. See you tomorrow.